Okay, so we're going to talk about section 5.3, or I'm sorry, 4.3. This is the fundamental theorem of calculus. This is one of the most important theorems in all of mathematics, and it starts with defining a function in the following way. So define the function, let's call it g. And g is going to be defined through an integral. So the input will be x, and that input will go up into the upper limit of an integral that we're going to do. And so we have some other function, f, and so this is the definition of g. So f is continuous, let's just say, on an interval from a to b, and x is any number between a and b. Okay, so so how is g defined? So let's just draw a picture of what a possible f might look like. So here's maybe a, and here's b. I'm just going to draw any old continuous function here. So this will be the graph of f. So f of x here. Notice in the integral we use t. Remember, it doesn't matter what letter you use in the definite integral. This is a placeholder only. So what does this say? So x is any number in between a and b, and we're taking that number as input and we're putting it into the upper limit in this integral. So where is that? So here's, let's just, for example, x could be here. All right. Well, if we put x there, then the integral from a to x of f is just the signed area up to that point, okay? So whatever the signed area, g's output, is the signed area between a and x under the graph of f, okay? Now remember what signed area means. It means that the number you get here will be this area here plus this area here, and then minus this area here. Okay, so it will be the signed area trapped between f and the x-axis. Okay, so that is that's the setup. Okay, so the fundamental theorem of calculus, part 1, okay, says the following. It says that in this situation, so f is continuous on an interval from a to b, and x is any number, if g is defined in this way, then g is also continuous on the interval from a to b. So you're allowed to put any number in between a and b into g, and g is continuous on it. And g is differentiable on the open interval from a to b. That means g has a derivative for every value of x in between a and b. And moreover, g prime of x is just equal to f. Okay, so the derivative of this function is just gotten by taking the function f and plugging in the variable x. Okay, so this is what the fundamental theorem of calculus, part 1, says. And as I say, it's one of the most important theorems in mathematics. Okay, so let's think about the basic idea behind why this is true. So the basic idea behind the proof, the proof, okay, of the fundamental theorem of calculus, part 1. Okay, so remember what I said. This is a class where we ramp up the sophistication level of what we think about, and so I'm going to just tell you guys outright here that being able to prove, to explain the proof of the fundamental theorem of calculus part 1 is a super bonus problem. And this will be, I really should call this a super duper bonus problem, but we'll just leave it at super bonus problem for now. Being able to explain the proof of the fundamental theorem of calculus on the exam, either this coming exam or the final exam, will be worth a massive amount of bonus points on the on the exam. But here's the basic idea. This is not the proof, the whole proof, but it's the basic idea. So if you're interested in obtaining these super duper bonus points for this, you should look at the proof in the book and come visit me in my office hours and try to talk to me about it. There's a few details we're going to leave out, but this is the basic idea. So let's just draw a picture of the situation here. Here's the graph of f, and here's a point x on the graph. And so we have again, remember what g is. G is the integral, from a to x of the function f. Okay. Now, what is the definition? So recall, the definition of the derivative of g is the limit as h goes to 0 of the following ratio. It is g, and you plug in x plus a tiny number, subtract g of x, and you take this numerator, divide by h, and then you look at the limit as h approaches 0. That's how we define the derivative in the first semester. Now let's unpack this just a little bit. So what is g of x plus h minus g of x? All right, let's write this down using the definition of g. So this is a to x plus h. Maybe we'll put x plus h here on the graph as well. Of f minus the integral from a to x of f. Okay, so think about this in terms of the areas here. So this is the integral from a to x is, let's see, I want another color here. Do I have a pen? I do. So this is the, let's call this this 1, and then we'll call this 1. So that's this integral right here from a to x is just that area right there, that signed area right there. Now, this area from a to x plus h is all of 1 plus a little bit more area. So we get, do I have another color? I might. Okay, maybe this will show up, maybe it won't. It's all of this area as well, so we'll call this area 2. Okay, so this is 2. So if we just look at the region 2, all of that up from a, all of this signed area from a to x plus h, and subtract away the area from a to x, that would be the blue portion right here. What we're left with is we're left with just this sliver. So let's see if I could maybe reproduce that in a picture here. My graph looked something like this. Okay, we're just going to do a little representative graph. Same thing as before. Here's x plus h. And so, so we just want to indicate this area right here, this side area right here. This is, we'll call it 3. This is this. Okay, so if we just take this difference, this is just looking at the definition of the derivative, is if we take the difference of these two integrals, we're left with just the signed area under the graph from x to x plus h. Okay, now what is that approximately? So this area right here, if we look at a rectangle, so I've drawn a rectangle, and the height of that rectangle is whatever the height is there. So we've got x, and then we've got f of x. So the height of this rectangle is f of x, and the width of this rectangle is h. Right? This distance right here is just h. So if h is very, very small, very, very small, okay, very, very small, then this integral, or this difference right here, is approximately, just approximately, h times f of x. Okay, just approximately, right? F of x is how high that rectangle is, h is how wide the rectangle is, and so the area of that is approximately, it's not equal to, but it's approximately. You can tell that if this were a really, really, really thin rectangle, then the amount of area in that rectangle would be pretty much the area, the actual signed area under the curve. And so we use this approximation and then just divide. So we have g of x plus h minus g of x, divide by h, and this is approximately f of x, okay? And so if you take the limit of this, the limit as h goes to 0, well, that tells you that g prime is equal to f of x, okay? So this is the basic idea of the proof, okay? That is to take the definition of the derivative, see what that gives you in terms of signed areas, call the difference, that signed area, approximately the area of a small rectangle that has height f of x, and then divide away the h and take the limit. That's the idea behind the proof of this, okay? So as I say, if you can learn a few more of the details that go into this, and they're in the book, and you're welcome to come to my office and talk about them, then you will obtain super duper bonus problems on this, and you will make me very, very proud, because this is, as I say, one of the most important theorems of mathematics. All right. So now that we've done that, let's just go to the examples. There's hair on this paper, from my cats, of course. I just got done brushing them, and so there's hair all over my house. I hope none of you are allergic. All right, so let's do an example. G of x is equal to the integral from 0 to x of the function 1 plus t squared, all of that under a square root sign. Okay, simple, simple, simple. So this is, so f here would be the function 1 plus x squared, and then the interval ab would actually, this will be the interval from 0 to infinity, because this function is defined everywhere. And so we could choose any x in this range for this. And so g prime of x, the derivative of x, is just 1 plus x squared. This is by the fundamental theorem of calculus. Okay, so the derivative of this function is equal to 1 plus x squared, the square root of that, by the fundamental theorem of calculus. Don't make these questions, that when you encounter them, too difficult. If you see this is how your function is defined, then the derivative of the function is just whatever's the function is in here in the integrand. All right, so let's do another example. Suppose g of x is equal to the integral from 0 to x sine squared of t, and that means that the derivative of g is equal to, well, just take your x here, put it in for t there, you have sine squared of x. Okay. Another example. Let's make it just a little more complicated this time. I'm going to take the function, let's call it something else here. Let's call it h, capital H. Capital H of x will be this function here, the square root of 1 plus t dt. Okay, you see what I've done here. I've made this a little bit more complicated. Okay, so it is not true that the derivative of h, so not true that the derivative of h is equal to 1 plus x cubed. That would be what you'd want to do, right? From the previous examples, all we did was take what was up here, put it in for t in each of these integrands, and that was the answer for what's the derivative of this function. Here, the answer is not quite that, okay? And why is it not quite that? Well, notice h is equal to, pardon me, h is equal to a composition of two functions. It's this, where g is the function integrate from 0 to x, the square root of 1 plus t. Okay? Do you see how this is true? So if g of x is this function, then g of x cubed is what you get when you take this x cubed and put it there. So we get 0 x cubed 1 plus t dt. Okay? So this is a composition. So in order to do take the derivative of a composition of functions, we have to use the chain rule. So chain rule. Okay? So what does the chain rule say? It says that if you have an inside function and an outside function, then you get the derivative by taking the derivative of the outside function, leave the inside function alone, and then you multiply by the derivative of the inside function. So this is what the derivative should be. Okay, how does that differ from what we wanted to do here? Well, g prime, g is this. We know what the derivative of g is. It is just taking x and plugging it into this function. So we get 1 plus inside of a square root. And now we put what's here there, but the input left alone inside of g prime is x cubed. So we take x cubed and put that in there, and then we multiply this whole thing by 3x squared. Okay? This is how you take the derivative of a function that's defined using an integral, but when there's another function here. Okay? Let me give you the general rule for this. So the general rule, and this uses the chain rule. It says that if you've got a function that looks like this, so if instead of having just x up here, you have another function of x, then the derivative is equal to, well, you take this function here, plug in g, and then you multiply by the derivative of g. Okay? We'll see lots of questions like this when we work on them in class. All right, let's try another slightly more sophisticated example. Well, let's do one more where we apply the rule here, and then we'll try another slightly more sophisticated example. So if you wanted to take the derivative with respect to x of, let's say, this function here, sine of x, and let's do the square root of 1 plus t squared. So if this is our function, we want to take its derivative, then we take the function here, plug it into the integrand, so we get 1 plus sine squared of x. That's what you get when you take this and plug it directly into the integrand. And then we multiply by the derivative of that function, so that would be cosine of x. So this is an example using this rule. The previous example also used that rule. All right, let's do one more example where we change it up just a little bit. How about the integral of sine squared of t? And now instead of putting the x up here, I'm going to put it down there. Okay. The question is, what is the derivative of g? All right. Well, this is actually just a little trick that I'm going to show you guys. Notice so if we'd really like for the x to be up here, okay, but it's not up there. So how can we modify this integral so that the x is up here? Well, if we take a look, we'd like for it to be, so we almost have this as true. But it's not true. If you reverse the order of integration, or I'm sorry, the limits in this integral here, what that does to the integral, if you remember one of our rules from the previous lecture, is it changes the sign of what you were integrating. That is, so this uses the fact that the integral from a to b of f is equal to minus the integral from b to a of f. Okay? Flipping the limits in an integral changes the sign of the integral because you're integrating backwards. All right, so now we can answer this question. So in order to take the derivative of g, well, let's just take the derivative of both sides of this. So we take the derivative. The minus sign is just a minus sign, so we can take the derivative. The minus sign comes along. And then here, we take the derivative on this side. Well, there's just an x there. We just plug that x in here, like so. Okay. Now this isn't quite our answer. We're looking for g prime, but we can do that just by multiplying by minus 1. Okay, just a little trick. You may encounter parts of the book that ask you this question. Okay, so that is the fundamental theorem of calculus, part 1, and its applications. All right, now let's talk about the fundamental theorem of calculus, part 2. This is sometimes called like the evaluation theorem or something like that. So here's what it says. It says if f is continuous on the interval from a to b, then the integral of f from a to b can be obtained by taking any antiderivative. This is probably a version that some of you who've seen any calculus before have seen. Then you can evaluate this definite integral by taking any antiderivative of little f and substituting b and a into it and taking the difference. So that this is where f of x, big F, is any antiderivative whatsoever. Of little f. Remember what that means. That means that, so to be an antiderivative means that when you take its derivative, you get little f. Okay. Let's see this with an example. So, example, how about the integral from -2 to 1 of x cubed? Okay. Well, in order to do this, we need to find an antiderivative of x cubed. Well, we know how to find an antiderivative of a function which is a power function. All you need to do is raise the power by 1 and divide by the new power. So dividing by 4 gives you this. So this, if you take its derivative, is equal to x cubed. So 1/4 x to the 4th is an antiderivative of x cubed. Okay, right? Just easy. So we can plug this in. So let me show you a little bit of notation that we use for this. So this is our standard notation. We write the function, the antiderivative. We draw a large bar. At the bottom of the bar, we put the lower limit of the integral. At the top of the bar, we put the upper limit of the integral. And that means this bar with the two numbers here means plug in that number into there, and then subtract. So we take 1/4 times 1 to the 4th minus 1/4 times 2 to the 4th. I'm sorry, minus 2 to the 4th. And we perform this calculation. So that is 1/4, and then let's see, minus 2 to the 4th is going to be 16. So 16 divided by 4 would be 4. So we're subtracting away 4. Okay, and whatever that is, it's minus 3.75. Okay, so that is the answer and an example of how we evaluate this in an integral of this form using the fundamental theorem of calculus. All right, let's do another example here. How about the integral from 0 to pi over 2 of cosine of x? Okay. Well, here, okay, again, all we need for to apply the fundamental theorem of calculus to this question is an antiderivative of cosine, and that is my vocal slip there is sine. Okay, sine, and then we evaluate this from 0 to pi over 2. Sine of pi over 2 minus sine of 0. Okay, sine of pi over 2 is equal to 1. Sine of 0 is equal to 0. So this is 1 minus 0, so it's 1. Okay, how do we interpret this? This is kind of cool. Cosine, oh, did I say pi over 2? I've been saying pi over 2. I meant for that to be a 2 the entire time. Sorry about that. Pi over 2, pi over 2, pi over 2. Okay, so 0 to pi over 2, so cosine looks like that. This is pi over 2 right here. This is 0. So what we've just established is that this area right here is equal to 1. Okay, that's the integral from 0 to pi over 2. This is the graph of cosine of x. The integral from 0 to pi over 2 is equal to 1, so that means that that area is equal to 1. Okay, very good. One more observation about the fundamental theorem of calculus, part 2. So we know that if we take the derivative of distance, we get velocity. Okay, so s here is a distance function. And it's any distance function. V is its velocity. Is its velocity. So we know that s is an antiderivative of velocity. So s and t is the antiderivative of velocity. So this tells us that if we integrate a velocity, then we can compute this integral by taking distance, plugging in the 2 time interval endpoints, and get the answer to this. So this is a very, very fundamental this is a very, very fundamental and physical application of taking definite integrals, and that is that. So this is the concept. Integrating velocity over a time interval is equal to the total change in distance over that time interval. Okay, I'll let you see that. Integrating velocity over a time interval is equal to the total change in distance over that same time period. Okay, this is a fundamental concept that I want us to all understand and how it relates to integration. Very good. We'll do problems related to the fundamental theorem of calculus in class.